Hey everyone, my name's Arnav, and I'm here to briefly go over the solution to the King's Guards from the 2021 NAC. So in this problem, you're given a graph and a set of guards, and each guard can go to some subset of cities in the land. The goal is to pick some edges in this graph and repair them. Then assign the guards to some vertex that they're allowed to be assigned to, such that every guard is assigned and every vertex is reachable by exactly one guard. Among all such ways to do this, output the minimum cost to repair the edges such that this is possible. Okay, so before we go into the specifics of this problem, let's talk about Metroids. So a Metroid is a structure which kind of generalizes the notion of linear independence. So, and this will give us a lot of useful properties and algorithms for free. You're almost definitely familiar with some Metroid, whether it be linear independence in linear algebra, spanning forests in graph theory, or maybe matchings. But a lot of topics in competitive programming are actually Metroids. So a Metroid is a collection of independent sets where all of these properties hold. So the empty set has to be independent. Every subset of an independent set is independent. And if there are two independent sets of different sizes, you can find an element that is in the larger set but not in the smaller set, add it to the smaller set, and still have an independent set. If you're familiar with these concepts from linear algebra, this should feel all pretty intuitive. What's cool about this problem is it is also usually a Metroid. So we're going to say a subset of edges in the input are independent if after considering all of these edges in our independent set, we can find a matching between guards and connected components in the graph that only use these edges, such that every guard is assigned to some component. Note that we're not explicitly using the perfect matching criterion here. There can be unmatched components in our graph, but every guard has to be assigned. Okay, so let's run through the Metroid properties and see if they apply here. So the first property, the empty set needs to be independent. Well, we can check this at the beginning by just running a matching algorithm between guards and vertices or villages. If one doesn't exist, then contracting vertices isn't going to help at all, so there's no solution. After that, if a set of edges is independent, and we remove some edges, we are still left with an independent set. The matching to components still works. Now we just have more unmatched components of villages. The third proof, where given two different independent sets, is a lot more involved. So that's what we're going to talk about over the next couple of slides. So let A and B be independent sets, and let G of A and G sub A and G sub B be the graphs after you contract the components using the edges in A and B respectively. Because A and B are independent, there's some matching between the guards and the components in G sub A and G sub B. So now let script C be the set of components in G sub A that can be unmatched in a maximum matching. Because A and B are independent and A has fewer edges than B, then script C has to be non-empty. It's not possible to match every component of script C simultaneously, because we know since there exists a larger independent set, there has to be at least one unmatched component in G sub A. Now consider one of these components such that B has an edge from that component to a guard. Then we can just add that edge, and we're good. Otherwise, all of the edges are either completely outside of script C, or they both have their endpoints in the same component of script C. So we can fix some matching of all guards to components of G sub B, and then find some component which isn't matched, and then take that edge. I know that was a really fast overview. I encourage you to pause this video and read over the slides. There's a lot of kind of different moving parts here, and a couple of different graphs you need to keep track of. All right, but uh, either you follow that proof or you're just going to take my word for it that this is a Metroid. The great thing about Metroids is they obey this kind of greedy property. So let's think about like Kruskal's algorithm for finding a minimum spanning tree. It's very straightforward. You take each edge in increasing order of cost, and if you can add that edge to your independent set, you do so. And checking if you can add the edge, that's where the disjoint set data structure comes in. But this kind of general concept of for each element in order, add it if you can, works for any weighted Metroid problem. So first we start with the empty set, then we sort the edges in increasing order of cost, and now we need to be able to tell if we add this edge to our set, is our set still independent? So to be independent, there's a couple of things we need to check. First, we never want to add an edge entirely within a component. That's just going to add cost, and that's never going to be worth it. So you can keep track of that with a disjoint set, just like Kruskal's algorithm. Then we want to see, is there still a matching if we add this edge between the guards and the components of villages? So kind of a very naive way of doing this is just for each edge, add it to our graph, run from scratch a bipartite matching algorithm. Let's say we use hop crop carp, which runs in e root v. Then our overall runtime is e squared root v. Unfortunately, e squared is e squared root v is like v to the fourth, v to the 4.5 in this problem, and with v equal to 300, this is too slow. So how can we speed this up? Well, we don't actually need to recompute the matching from scratch each time. We can instead find an augmenting path in the existing matching. So, like before, we keep the disjoint set of villages. We need to ensure that they're in different components. But we also now need to keep track of is there some way to unmatch this component. Then, unmatching a component can be done by finding an augmenting path in this bipartite graph. And doing this will run in big O of v, where v is the number of vertices. So the overall runtime is the initial matching to see if it's possible. Let's say e root v could be a little worse if needed. E log e to sort all of the edges. And then the number of vertices times the number of connections between guards and villages, which is guaranteed to be not too large, v squared. So overall runtime, you can say, is about v cubed, but you still need a careful implementation to get AC. Hope you enjoyed the problem.